Okay, so our project has to go through following these steps: image acquisition, pre-processing, grayscale conversion, edge detection, feature extraction, and after feature extraction, comparison and final output. So in out of these steps, uh, image acquisition and grayscales and edge detections are completed, uh, and the remaining following these, uh, which are most important among these, are remained. So let's see uh, image acquisition, grayscale conversion, and edge detection. Here is the image of cat that we see by our eyes, but how does the computer store this image? The computer stores this image is shown in second figure. The computer stores this image in form of pixels. When we zoom this image by any Photoshop app by thousands times, we can see this 2D grid, and each cell in this grid is called as pixel. Let's see more about pixel. So in each pixel there is information about color. So pixel is the smallest item of information in an image. In simple words, we can say that if element is consist of atoms, then picture is consist of pixels. So in each pixel there is value of RGB. So what is RGB? To find this answer of this question, we go back to our school times. In school we learn prism, and Newton proved that using that prism that white color is consist of 7 color with pure, and each 7 color has its frequency, but our eyes are most comparable with frequencies of red, green, and blue colors. So that's why there is information stored in each pixels of RGB. Here is one website which gives more about RGB. Here is one amazing website, RGB Explorer. By using this, you can get information how colors are made of RGB. You can get any color that you want by changing this cursor. It changes from 0 to maximum 255. When red is changed to 255, it gives correct red color. As well, we can add green in it. It gives blue. Again, if we change all 3 to 255, we get exactly white color. You can play with it and obtain any color that you want. If all are 0, it gives black, and if all are at maximum, it gives white. In between, you can get any color that you want. Now let's talk about grayscale image. It is an image and it's grayscale image. We already have seen what is grayscale image. Grayscale image does not give information about colors of image, but it gives information about intensity of that colors in that image. So why do we need grayscale image in image processing? In image processing, we need grayscale image for mainly two reasons. First is, in image processing, we don't require color image all the time. So if we use color image, then we need to work on larger data. So for simplicity, we convert it to grayscale so that we can reduce its complexity of our program. And another reason is, RGB image that we have seen earlier is 3-dimensional, while grayscale image is only 2-dimensional. So there are some algorithms that can be applied only on 2D image, like edge detection and feature extraction algorithm. So for that we need to convert image into grayscale image. How to convert RGB image into grayscale image? There are mainly two methods to convert RGB image into grayscale image. First is average method and second is luminance method. In first method, we take average of all red, green and blue, and second is luminance method. In luminance method, we take 30% of red, 60% of green and around 10% of blue, and this formula is made on the basis of how much wavelength of that color present in white light. So now we will see code for this. Okay, so Saurabh has written this code, and he has divided this code in three sections. First section is to take image, second section is for average method, and third section is for luminance method. So let's see. So imread is the command to take as input image. Here 100 rupee is the image in this map folder, and this is to pop up the window and show first row and third column. Title will give as original image. So this is will give the taken input and show it just. And second section is for averaging method. For that we have first convert 2D array, and for the number of rows and number of columns will give this by size image 1 comma 1 size image comma 2. So that this will give number of rows and number of columns, and zeros will create 2D array of size, number of rows and number of columns. So let's see average method. For this is for loop arranging from first row to number of rows, similarly first column to number of columns. For that, for each column and rows in 2D array, we take red value, green value and blue value. For that, our image ij comma 1 will give red, ij comma 2 give blue, green, and image ij3 gives blue. After adding this, we divide by 3, that is means multiplying by 0.33, 0.33 and 0.33. Now after converting this by averaging method, we show it on the output by this command. So this is section 2, and section 3 is luminance method. For luminance method, we take the same 2D array and multiply by our formula that we have already seen, multiplying by 30%, multiplying by 60% and around 10%, and showing that output. So let's see what is the result of this all code. So here is the original image. For that, this is averaging method and this is luminance method. Okay, so now we will see edge detection in image processing. So the main purpose of image processing is to find object, right? So edge detection is a technique for finding that object. So edge detection finds the object by finding boundaries of that objects within that image. So let's see more about edge detection. So here is the image of butterfly and its edge detected image. Here you can see how objects are, there is a butterfly is getting tracked, and you can see how butterfly and these leaves are traced from this grayscale image. So edge detection, this process is only applicable on grayscale image, and this gives output as edge detected image as this given figure. So why do we need edge detection in image processing. So we already seen that edge detection can be used to find objects. So edge detection reduces the amount of data in image. So for that, image detection makes easier for image segmentation and feature extraction algorithms that we will see in future. So for that also edge detection techniques are also used. So now we'll see the edge detection techniques. So there are two types: first order and second order. In first order there are Sobel edge detection, Privet edge detection, and Robert edge detection. And in second order there is a canny edge detection technique and Laplacian of Gaussian technique. So we will see one example of each. We'll see Sobel operator and canny edge detector. In between these two, canny edge detection gives better result. We'll see how to obtain edge detection using both these techniques. So first is Sobel edge detection. In Sobel edge detection, image is processed in x and y direction respectively, and this gives us new image, which is sum of x and y edges of that image. So in Sobel edge detection, we calculate gradient using Sobel kernels. So there are two kernels which are fixed for every image. Whenever we apply Sobel edge detection, we have to use same kernels, and from that kernels we calculate gradient of that image. We'll say example, we'll get it better. So here is Sobel X and Sobel Y kernel. So how this Sobel X and Sobel Y kernels are obtained? These are fixed for every Sobel edge detection. So in Sobel edge detection, Gaussian filter plays a vital role, because in Gaussian filter the center values are greater than the rest of remaining values. Here 2 is greater than 1 and 1, and this 1D Gaussian filter is multiplied with x derivative and y derivative, we get Sobel X. When 1D Gaussian filter is multiplied with x derivative, we get Sobel X kernel, and y derivative is multiplied with 1D Gaussian filter, we get Sobel Y filter, Sobel Y kernel. So let's see this example. So in Sobel edge detection, we have to calculate gx and gy to calculate gradient. So consider this is an image and it's a RGB value after converting grayscale image into grayscale image. Now for every pixel we have to calculate gx and gy to calculate gradient. But for pixels that are on boundaries, we can't apply this 3x3 matrix, because there is no because we have to match this center to this pixels, like this 0 should be matched with this pixels. So when we put this matrix 3x3 matrix and on this image to calculate gx and gy for these pixels, we get gx is equal to 1 into 100, 0 into 100, minus 1 into 50, 2 into 100, 0 into 100, minus 2 into 50, and so on. So after calculating gx, we get 200, right? Similarly, we have to calculate gy. So when we Sobel y is multiplied on this image for calculating gy at these pixels, we get gy as 0 after all multiplications, and gradient of these pixels is equal to g is equal to under square root of gx square plus gy square plus gx square plus gy square. And after calculating gradient value, we have to compare with threshold value. If gradient value is less than threshold value, it should be replaced by threshold value, and if gradient value is greater than threshold value, it should be keep as a gradient value. So let's see code for Sobel edge detection. So this is code. Here reading image which is available in this folder, showing on this output console. Now this is RGB to grayscale conversion inbuilt functions, but here we will replace the code of part that we have seen earlier, conversion of image to grayscale image. So we will replace that here. Again, converting image to table for more precision. Now we will require two-dimensional array to store values of gradient as same dimension as image. For that we require temporary array. Now this is Sobel X, Sobel Y operator, which are fixed for every image processing by using Sobel edge detection. Now we iterate through image from number of rows and number of columns. Now we need to find G of X and G of Y. For that we are iterating 3 by 3 matrix. So row plus 1, row plus 2, column plus 1, column plus 2. So we iterate to this size of pixels and multiplying with Sobel X operator. Similarly Gy for Sobel Y operator. After finding G of X and G of Y, we calculate gradient. Gradient is equal to square root of G of X square and G of Y square. So we calculate gradient and store in our temporary array. So this is filtered image. This is shown as filtered image. Now last part is comparing with threshold. Now threshold value is decided by us, so it can be 0 to 255. So I have considered 100, and this is compared with our filtered image. If the gradient value is greater than threshold value, it is considered as it is, but if gradient value is lower than threshold value, it is replaced with threshold value, and we will show is edge detected image. So let's see how is the output. So here is image. So here is the input image, which is filtered and is compared with threshold value, and we get edge detected image. So edge detected image is little bit blurred, so we will see how Canny edge detector is applied to get clear edge detected image. Now we will see Canny edge detector. Canny edge detector was 7 to 8 steps, and Canny edge detector gives better result because Sobel edge detector have limitations, like Sobel edge detector does not detect edges in diagonally directions. It only detects in X direction and Y direction. So, and second reason is Canny edge detector is highly sensitive to noise. So let's see how Canny edge detector is better than Sobel edge detector. So there are 7 to 8 steps. First step is conversion to grayscale. We have already seen this. Second step is converting to Gaussian blur. So Gaussian blur removes some of the noise before further processing the image. Third step is intensity gradient calculation. So we have this step also we have seen how to find gradient from Sobel X and Sobel Y. But, so up to this we have these steps are common in Sobel edge detector, but this is not sufficient. By using Canny edge detector, which we are going to obtain in next steps, using this we can predict not only edges but it also its directions. So for that we have to calculate theta. So step 4 is calculation of theta. To obtain theta, we take inverse of tan of gy by gx. By using this, we calculate angle theta. After finding angle theta, we need to adjust this angle because at pixel level, which is almost like we have to zoom it 1000 times to get pixel level image. So if angles are not exactly 90 degree, 45 degree or 135 degree, then we need to approximate it. So imagine this is pixels of image and we are considering this pixel. So there can be possible directions like 0 degree, 45 degree, 90 degree and 135 degree. So if there is a theta if like 40 degree, then we need to convert it to 45 degree. So there are 4 rules to convert these angles. If angle is between 0 to 25.5 or 175.5 to 180, then we need to convert it to 0. If angle is 22.5 to 67.5, then we need to convert it as 45. Similarly, if the angle theta is between red portion, then we need to convert it as 90 degree. If theta is between yellow portion, we need to convert it as 135 degree. So we will see code for up to this part. So this is our code. First step is conversion to grayscale image. So here we will replace the conversion of grayscale image. So I have decided to make code by segment. So to understand better and reduces complexity. Now up to this part, we will replace the result of grayscale conversion of image to grayscale image part. But in this part, I have used inbuilt function to reduce size of this code. So here we get grayscale image by using this RGB2 gray inbuilt function. Second is operate with Gaussian blur. So here is Gaussian filter coefficient and filter that need to be convoluted with our image. We add same number of rows and number of columns of our image. Third step is intensity of gradient calculation. So here are Sobel X and Sobel Y operators that need to be convoluted with our image to get g of x and g of y. Now fourth step is calculation of theta. We get array of values of inverse of tan by using this inverse of tan functions, and here we convert it to angle. Now this angle should be approximated to 0 degree, 45 degree, 90 degree and 35 degree. For that we need temporary array, 2D array. So size a by 1 will give number of rows and size a by 2 gives number of columns. And now in these two for loops we iterate to our array, and if the angle is negative, then we convert it to positive by adding 360. And here is the logic for converting 0, 45 degree, 90 degree to 130 degree. If the angles are, that is, we have seen 4 rules how to convert angle to 4 multiples of 45. So here is the logic. if else statements, and in temporary array we store this angle value. So remaining steps are non-maximum separation, thresholding, and edge tracking. So sixth step is non-maximum separation, as name suggests. In these steps, we are going to suppress edges which are not maximum. That is, we need to suppress pixel to 0, which cannot be considered as an edge. So after sixth step, we get this type of uncleared image, and this need to be made clear by using thresholding and edge tracking technique. But problem is I could not write logic after this part, and I need to spend more time to write MATLAB code. I understood the concept, but I'm not able to write the code from this part. But I will show a result by inbuilt Canny edge detection by Canny method. So if you use inbuilt Canny edge detection function, then we will get result. Wait, yes. So if we use Canny edge detector, then we will get this type of image. So I will write code for remaining 6, 7 and 8 steps. Thank you.